What you're looking at is one of the most powerful algorithms in statistics. It's often touted as a solution for missing data. The algorithm is so useful that it's been applied to problems far outside of statistics. Despite this, it's not very well known. So in this video, I want to teach you about this amazing thing called the EM algorithm and tell you a little bit more about how and why it works. If you're new here, my name's Christian and this is Very Normal, a channel for making you better at statistics. Let's get started. To really understand what the EM algorithm is about, you first need to understand a fundamental idea in statistics, the method of maximum likelihood. So to start, I'll develop a basic example to teach it, and then we'll take an extra step to see how the EM algorithm is involved. This example deals with subscription-based platforms like Netflix or Brilliant. These platforms care a lot about how long their subscribers stay as paying members. If they know how long someone will stay and pay, they'll be able to make better revenue forecasts and plan better for the future. For simplicity, we'll refer to this metric as customer lifetime. Let's say that I'm a project manager for a fictional tech company called Kinda Normal. The CEO, Mr. John Normal, has asked me to determine the average customer lifetime of recent subscribers. And being the good manager I am, I ask one of my data scientists to handle it instead. We'll call him Roger. I ask Roger to devise an experiment to answer our CEO's question. And after some thought and planning, this is the design he executes. Roger figures that the best way to get high quality data on this group is to start with a new set of subscribers and just wait. That way he can calculate the lifetime for everyone directly, since he'll know when they start and when they end their membership. Roger knows this approach is going to take a long time, so he only chooses 10 people to track. After many months of waiting, Roger sees these lifetimes. This is where statistics comes in. To the untrained eye, data might seem like it's just a bunch of numbers. But to statisticians, we know that data comes with extra baggage. Data is troublesome because it's inherently unpredictable. Roger had no way of predicting what lifetimes he'd see, so the only thing he could do was wait until the last person left. Furthermore, data is random. If Roger were to gather data on 10 other people, he'd probably see different numbers. To learn from this data and answer the CEO's question, we need to account for these qualities in the data. In statistics, our answer to this is mathematical models. They're models in a sense that they're approximations of the real world. But even if they're just approximations, we can still benefit from being able to learn from them. One model we can use for this data is the exponential probability distribution. In general, probability distributions describe what data values we're likely and unlikely to see. When this function is larger, we're more likely to see the data value associated with it, and less likely when it's smaller. In our case, we have a particular type of data called time-to-event data, which is only positive and continuous. The exponential distribution gives us a useful model for data that's like this. But it might not be very clear how we learn from this model. To understand that, we need to understand parameters. The exponential distribution is what we call a parametric probability distribution, or just parametric distribution for short. Generic probability distributions can have really complicated shapes. But with parametric distributions, the entire shape of the distribution is decided entirely by a few numbers called parameters. Here, I'm denoting the parameter for this exponential distribution as theta. If I change the value of theta, you can see that the shape of the distribution also changes, which by extension dictates what lifetimes we're unlikely and likely to see. In many cases, these parameters also have intuitive interpretations. This operation is called an expectation, a fancy name for a special kind of average. For the exponential distribution, theta actually represents the average lifetime that would be generated. And it's exactly what Roger and I want to know. But there's a big issue. We don't actually know the true value of theta. That's what we're trying to figure out in the first place. What we do know are the data that Roger collected. In our model, we assume a particular value of data establishes the distribution that generates the data we see. So while we don't know what theta is, the data that come as a result should reasonably be used to make an educated guess. In statistics, we call this process estimation. So our goal is to estimate the average customer lifetime using these 10 observations. A natural next question is how? How exactly do we use the data to make a guess for the data that produced them? There are a few ways to do this, but the one that we're going to learn is called maximum likelihood estimation. To start, we'll look back at the function behind the exponential probability distribution. Just for demonstration, let's say that the average customer lifetime is 2 months, so data equal to 2. The first lifetime in Roger's data was 3 months. We could plug that into this function. The resulting number isn't exactly a probability, but it can roughly describe how likely we are to see a lifetime of 3 months, relative to the other possible values. But here's another perspective. What if we fixed the value of the lifetime instead and looked at this expression as a function of theta? This is what that function would look like. If the probability distribution function describes what lifetimes are likely and unlikely, what if we applied that same logic to this new function of theta instead? Just by looking at it, you can tell that the maximum of this function happens at around 3. And spoiler alert, it actually is 3. Let's think about that for a little bit. Theta represents the average lifetime. So if theta were actually 3, then that's a typical lifetime you might observe in the data. Other values of theta can produce a lifetime of 3, but they're just less likely to do so. The maximum suggests that a theta of 3 is most likely to produce a lifetime of 3, so maybe that's a good guess. That would be the case if we were only considering a single data point. But if I were to repeat this process with the other 9 data points, then we'd get 9 other functions, each being maximized at a different point. It's not very helpful to have 10 different guesses to what theta is. Ideally, we'd have one guess for theta that encompasses all the data we collected. Instead of working with 10 functions, we can combine them by taking their product, which results in this function. This function is so important to statistics that it's been given a special name, the likelihood. Different datasets will cause the likelihood to take different shapes, and this shape is going to help us make an educated guess for the parameter theta. You already might be able to guess how we do that. After constructing the likelihood based on the data we collect, we can pick the value that maximizes it as our guess for the true value of theta. This entire process is called maximum likelihood estimation, and it's a fundamental method in statistics. While I can't do it full justice here, I've put a link to a more dedicated video in the description. Without going into the details, the value that actually achieves this maximum is the average of the data we collect. So given this data from 10 people, we estimate that the average customer lifetime of the Kinda Normal user base is 3.37 months. And that makes sense. The average of a subset of subscribers should be a reasonable guess for the average of the entire member base. And this intuitive answer is backed by statistical theory. We won't always have a nice formula for the maximum likelihood estimator, but as long as we have a way to figure out what the value of this maximum is, we can still use the method. Now that you know about maximum likelihood estimation, you're ready to take on the star of the video, the EM algorithm. So let's pick up where the first experiment left off. Okay, finally I'm done with my experiment. Based on 10 new subscribers, I estimated that our average customer lifetime is about 3.3 months. Roger, it's been almost a year and we only have data on 10 people? Kinda Normal has thousands of users. We're gonna need a lot more data than that. Right, I see you and I hear you, boss, but it can take a long time for someone to leave. One person in the data stayed for over 11 months and I didn't want to lose their data. It's just not feasible to collect complete data for thousands of people. Roger has a point. You'll just naturally lose people if you can't wait long enough for them to unsubscribe. On the other hand, we do need to draw a line somewhere. We need a better experiment that can account for both of these problems. After a little bit of pretend thinking for the sake of storytelling, I get an idea. I tell Roger to start a second experiment, but this time, I tell him to gather 1,000 new subscribers for the sample. To address Roger's concerns about waiting too long, I tell him that he can stop the experiment after just 6 months. No more, no less. Furthermore, I tell him that all he needs to check is whether or not these 1,000 individuals are still on the platform. Roger is of course skeptical, but I assure him that it'll all work out.
6 months later.
Roger reports back that 593 people left the platform, while the other 407 stayed. These numbers may sound weirdly specific, but I'll explain why later. In an ideal world, we would have gathered the lifetime data from all these people, which would have let us use maximum likelihood. Unfortunately, we live in the real world, but at least the real world has the EM algorithm, so let's get into it. You can think of the EM algorithm as an expansion pack to maximum likelihood. It lets us do maximum likelihood even when we're missing data. Theoretically, if we were going to use maximum likelihood, then this would be the likelihood that we would use. This first product represents the likelihood from the first experiment that Roger did, and we're still using these X's to denote that. The second product represents what would have been the lifetime data from the second experiment. I'll use Y to denote these observations. The reason that we can combine the products in this way is because the two experiments are reasonably independent of each other. The X's are lowercase because we've actually observed this data. The Y's are uppercase to indicate that we haven't observed them, but they're still random quantities. And since we're using the exponential model for the entire platform, the same data is used throughout the expression. I'm going to call this the complete likelihood. And even though we're missing these observations, this function will still come in handy. With this complete likelihood in mind, we also have a notion of a complete dataset. I'm going to denote this complete dataset with this fancy D. But what we have instead are whether or not each person in the second experiment was around after 6 months. These S's represent stayers. If a person was around at 6 months, then their particular S value would be yes or 1 and no otherwise. The X's and the S's form what I'll call our observed data, and I'll distinguish it from the complete data by denoting it with a fancy X. With these three ingredients, we can try to apply the EM algorithm and overcome our missing data problem. The EM algorithm is a cycle of just 2 steps, the E step shown here and the M step shown below. The E stands for expectation and the M stands for maximization. I'm going to give a high-level intuition for each step, and then we'll ground this intuition and see how it can be applied to our example. The E step says we need to derive a new function from the complete likelihood. This new function, Q, is also a function of theta, but it also relies on a previous value on theta, which I've written as theta t-1. If we're just starting the algorithm, we can pick some initial value and let it rip from there. I admit the notation can be pretty intimidating, so I'm just going to state what it is in as plain of language as I can. The Q function is the expectation of the log of the complete likelihood conditioned on our observed data. And somehow, this function overcomes our missing data problem. Once you derive this Q function, we go into the M step and find the value of theta that maximizes it. But it's on this Q function instead of the complete likelihood. What we get is a new value of theta, and we start the cycle all over again. The cycle of E and M steps continues until the value of theta we see converges to a stable value. And this stable value will become our maximum likelihood estimator. That's the EM algorithm in a nutshell, but I'm sure it's not that helpful to just hear it in words. It'll help a lot more to see how the algorithm applies to our example. For demonstration purposes, I've simulated some data for both experiments, so that's how I knew the specific numbers of stayers and non-stayers. This means I actually have access to both the quote-unquote observed and complete datasets, which we normally wouldn't in real-world circumstances. Thankfully, the EM algorithm doesn't care if the data is real or not, just that our models are correct. You don't need to understand this code directly, but just know that it gives me a dataset that will let me visualize the EM algorithm working in real time. The whole point of maximum likelihood and the EM algorithm is to craft an educated guess for a parameter, which governs the randomness in the data. Because I made the data, I also know that the true value of the parameter is 12 months, because that's what I set it as. For reference, I'll represent it with this ghostly red line. If the EM algorithm truly works, we should see the estimate crawl closer and closer to it. We're going to start with an initial value of 2. Starting from the complete likelihood, we need to take its logarithm and then calculate its expectation given our observed data. This would be the resulting Q function. The calculation isn't fully complete, but I wanted to stop here just to point out how the E step helps us overcome the missing data problem. In the complete likelihood, these missing lifetimes prevent us from using maximum likelihood estimation. But in this Q function, we're effectively replacing all the random and missing elements with their conditional expectations. Since we theoretically know what these numbers might be, we're replacing missing values with known values. Let's zoom in on what these conditional expectations would be for our particular example. At first glance, this expression makes it seem like we have to condition on a lot of different things for each person. All the data from the first experiment and all the data from the second. In reality, a lot of this can be ignored using standard statistical assumptions. For instance, all of the data from the first experiment can be ignored because the 2 experiments are independent. Furthermore, we also assume each person within an experiment to be independent from each other. This lets us ignore all the other S's except the one associated with each person. For people who are still around at the 6-month mark, this would be their conditional expectation, and for people that aren't around, this would be theirs. I'm skipping the math here, but both of these expressions can be derived from the fact that we're using an exponential distribution as our lifetime model. However, to calculate either of these expectations, the value of theta needs to be fixed beforehand. So we can use the previous value of theta as a placeholder. Looking back at our Q function, we need to split the sum up. So we have 593 instances of this conditional expectation. Likewise, 407 have the other expectation. If we were to roughly plot this function, this is what we'd see. You can clearly see that the maximum is different from our initial value, so we need to figure out what that is with the M step. And we can actually derive a formula for the maximizer through standard calculus techniques. The M step tells us that it takes on a form similar to a weighted average. And once we plot it, you can see that it really lines up with the maximum of the Q function. It also takes quite a big step towards the true value, so that's good to see. From there, we just keep iterating. E step, M step, E step, M step, repeating until convergence. With enough iterations, you can see that the estimate converges and stops moving, so we can stop the algorithm. Our final guess for the customer lifetime is about 11.6 months, which is pretty close to the true value of 12 that I actually used. So we were able to derive a pretty good guess despite the missing data. Before we move on, I want to say that this is a specific use case of the EM algorithm. The complete likelihood, complete data, and observed data have specific forms here, but they could look completely different with a different model and different data. But what won't change are the principles that undergird the EM algorithm. Maybe it's satisfying the CA work for a specific example, but how do we know that this procedure will work in more general cases? To understand that, we need to understand the connection between the two main functions at play here, the complete likelihood and the Q function produced by the E step. It can be shown that the complete likelihood is actually lower bounded by this Q function. More specifically, lower bounded by the Q function plus another value that doesn't depend on theta. Therefore, it's enough to just maximize on the Q function and ignore the second constant. This property will hold regardless of what situation we're in. At one point in our simulation, we got a Q function that looked like this. By definition, we know that the M step will give us a new theta that either increases the value of the Q function or keeps it about the same. Thanks to the lower bound, it has to be the case that the complete likelihood at this new value of theta is either going to be higher than the Q function or the same value. So by maximizing the Q function, we're sort of pushing up on the complete likelihood from below, even though we don't directly know what it looks like. The EM algorithm was popularized by the landmark paper by Dempster, Laird, and Rubin in 1977, though the authors note that it existed in various forms prior to their paper. This paper was so influential that according to a 2025 analysis by Nature, it's currently one of the most cited papers of all time. And that's a testament to how powerful this algorithm is. The example I concocted for this video was actually adapted from a great article in the American Statistician called Exercises in EM. I've put a link to it in the description, as well as other useful articles I used in researching this video. If you enjoyed the video, I hope that you'll subscribe to the channel for more content like this. You can stay up to date by signing up for the channel newsletter, where you'll get notified every time I upload a video. This was my entry for the Summer of Math Exposition. I hope that you learned something new today. Thanks for watching.